homework quiz would do it with perfect accuracy. So, on this first evaluation, and the biggest thing when you're evaluating is the nerve of, okay, I'm putting in negative numbers again, because as we saw in the homework quiz, that's what caused the majority of the mistakes. So, like I said, when you do that, use parentheses. So you're going to put negative 3 squared to replace that x, minus 4. Now this is a little tricky. The parentheses are essential when we're dealing with exponents, absolutely essential. They're not as essential with just addition and subtraction because those double sign rules do apply. And right here, quite frankly, and again, it depends on how comfortable you are, I probably wouldn't enter another set of parentheses around the x just because parentheses within parentheses, if I can avoid it, if I know that those parentheses aren't really necessary, I will avoid it. But again, it's what you're comfortable with, and just knowing that the exponent makes a big difference. Sometimes basic subtraction does not. So I would just do negative 3 minus negative 5. And then slowly going through, parentheses, okay, that's right here. So negative 3 minus negative 5 is what, Alexa? 2. Negative 3 plus 5 is 2, correct? And while I'm there, I'm just going to replace that with 2. I'm also going to do the next step because it's kind of separated from all this other stuff. Negative 3 squared, that's an exponent. So Corey, where's Corey? What's that? What's negative 3 squared going to turn into? Positive 9, very good. If you didn't have those parentheses there, technically, and maybe you would mentally end up on the right side anyway, but negative 3 squared versus negative 3 squared. Big difference. In fact, your calculator will tell you it's a big difference. Because without the parentheses, battery's low, no batteries. Negative 3 squared, without the parentheses, negative 9. Negative 3 squared with the parentheses, positive 9. Could anyone explain why that is? What's your first name? Bella, go ahead. Wow, that was really well done. I'll illustrate with you what she's talking about. Without the parentheses, you're really only squaring that 3, so it's a negative 3 times 3. With those parentheses, you're actually squaring negative 3, so it becomes negative 3, a double negative. Negative times a negative is a positive 9, and this one she kind of said it in a nice way as well. It's kind of just bringing the negative along with it. It's whatever you're squaring, and the negative is just always going to be out in front. So this one is negative 9. Okay? Literally one of the most common mistakes from 9th grade right on through to calculus. And then once we're down here, we have 9 minus 4 times 2. Obviously, in PEMDAS, multiplication would come next, so 9 minus 8, and our answer here is 1. Okie doke. Why don't we go ahead and try that next one on our own. that is, you didn't really need to simplify anything. That was simplest rational form. So 2 times negative 2 squared plus 3 over, and this is x times y, so we definitely do want parentheses there to indicate the multiplication, minus 2, and we do want parentheses there to indicate multiplication. So 2 times 4 is 8, plus 3 is 11. And then down here we've got negative 6. And then the double negative here will be plus 4. And we have 11 over negative 2. Negative 11 halves. Now, this is funny to me. Raise your hand if you think this is the same or different than this. Okay? If you think those are the same, I want you to hold up a 1. If you think those are different, I want you to hold up a 2. On your mark, get set, go. The idea is not to look around at what everybody else has and then... Okay. So you're just auditing the rest of you. There's a very solid mixture out there of people who think it's the same and people who think it's different. Well, let me give you a way of testing. If I type on my calculator 11 divided by negative 2 versus negative 11 divided by 2, same or different? Same. So those of you who held up a number 1, good job. Those of you who held up a number 2, even better job today because you learned something, right? Good job. Not only that, but I'll also mention that oftentimes the negative is just flat out in front. That's also the same thing. Okay? Here's what's different. Maybe that's too wide open of a question. None of these all equal each other. None of these equal that. Who can explain why? Go ahead. What's your first name? Kaylee? Haley. Go ahead. Right. 2 negatives make a positive. So those double negatives, this particular one, actually would equal positive 11 halves or 5.5, not negative 5.5 like we're looking for, okay? So again, a common mistake from algebra, but not even algebra 1, pre-algebra, 8th grade probably, all the way up through calculus. We just can't get away from that. So hopefully you've committed that to memory. This one gets ugly because of really the sets of parentheses, and we get a little bit more into distributing here. So on a problem like this, where should we start? Where should we start? Where's Kate? Where do we start, Kate? Where would you start? Very, very good. Distribute the negative. When you have parentheses, inside brackets, and so on, you want to kind of start as inside of that as you possibly can. So we're thinking the parentheses within the brackets. You can't reduce within those parentheses, but we can eliminate those parentheses and make it look a little bit less confusing if we just distribute this negative. So I want you to show that. And I'm going to leave everything else the same, keep my bracket, but I'm going to change this to 8 minus 2y plus 4. Because there's a double negative there. I'm distributing a minus to a negative 4, and it becomes plus 4. Now, you have a couple options here, and either order you do it in is fine. Within those brackets, now, I can combine the 8 and the 4 if I'd like, or I could just distribute now the negative 5 to all 3 of those terms, and then worry about combining like terms at the very end. I'm going to go that way. I'm just going to get the distributing and the brackets out of the way. Then I'll worry about combining like terms. But either way, it would turn out the same. Keep in mind here, I'm not distributing a 5. I'm distributing a negative 5. So any sign issues that we have to deal with multiplication, keep those in mind. So I've got my 6. Oh, you know what do you think people do all the time in a problem like this? That common mistake that's 8th grade through calculus? Does anyone know? What I see a lot makes me cringe. Yeah. Yeah, they do 6 minus 5 because it's so inviting, right? We all know that 6 minus 5 is 1. That's what you see, and then they distribute the 1, and that would definitely not give you the right answer. So again, come back to PEMDAS. So we've distributed, kind of getting rid of parentheses. You never, ever, ever do subtraction before multiplication. Okay, so this is 6 minus 5 times a set of brackets. The 5 times a set of brackets is going to come first. So 6 minus 40. The negative 5 times the negative 2y is going to be a plus 10y. And the negative 5 times the positive 4 is going to be a negative 20. And then 3 of those terms can be combined. So we've got a negative 40 and a negative 20, which makes negative 60, right? And negative 60 plus a positive 6 is going to put you at negative 54. So negative 54 plus 10y. To be truthful, usually, and you guys probably remember this from Algebra 1, polynomials, you'll usually see like the squared term first, and then the x term, and then the final term. So this would probably be written as 10y minus 54. And it's critical, just like the previous example with fractions, it's pretty critical that you understand that those are the same things. Okay, as long as that 10y is positive, obviously in the second expression we don't need to write the positive out in front, and that the 54 is negative, which shows up in the second expression as a minus 54. But understanding for sure that those are the same thing. Okay? On number 2, we have a lot of time here, so I'm just really taking my time over explaining these. I'm actually glad I do have more time today. Why don't you try number 2 on your own? Where is Owen? Owen. Loud and proud, tell me what you have as your answer. Listen carefully so you can check whether you agree or not. Okay, take another minute to finish. Keep it going. Raise your hand if you are done. Eric, are you done? Can you read your answer nice and loud so we can all hear it? Can you bring me your paper? Faye, can you read me your answer? You can close that out. Can you bring me your paper? Haley? Can you bring me your paper? Who's really confident in their answer? Vince, you're my only guy? What do you have, Vince? bring me your paper? Does anyone have a 70 in theirs? Yes. Chloe? Are you the only one that has a 70? No one else has a 70 in theirs at all. Chloe, read your answer, please. You're my only hope. We're better, but no cigar. Shoot. Okay. So I just want to take a quick peek at what our mistake was. Okay. Let's look at a few of these that I collected. Here's what this person did. They started here, I believe. They got 6x to the third, golden, minus 14x, wonderful, plus 3x squared, and minus 7. So they multiplied those first. My question is, it's 5x cubed times all of that. Where in God's green earth did the plus sign come from? Do you see that? How we inserted that? So it shouldn't be 5x cubed plus this. It should be 5x cubed times all of that. Correct? Okay. Okay, this person did maintain the multiplication. Their issue, 2x times 3x squared, should have been 6x cubed. Other than that, they're pretty good, and because they had that as a squared term, they combined it with the 3x squared, which they actually are not like terms in reality, so they shouldn't have been combined, and then they stopped. They actually should have continued to distribute that 5x cubed. Okay, so I think we've got the gist of the issue. Again, here this person inserted a plus sign. I expected to see this one too. This person did something totally different. They distributed their 5x cubed to this, getting that, and they distributed their 5x cubed to the other binomial as well, and then they added everything together. Okay? Let me back up with you guys for a minute. If I told you 2 times 3 times 4, do you multiply the 2 times the 3 to get 6 and the 2 times the 4 to get 8 and then multiply those? Absolutely not. If it looks like this, then you distribute, because 2 is being multiplied by the parentheses, therefore everything in the parentheses. Here, 2 times 3 times 4 is just 2 times 3, which gives you 6, and then 6 times 4, which gives you 24. And we all know that this can really be done in any order. I could, if I wanted to, depending on the numbers, and it was easier for me, 2 times 4 is 8, and 8 times 3 is 24. That's a commutative property, right? You can do multiplication in any order that you want to, but you distribute when you see a plus sign. You do not distribute when you see multiple multiplication signs, okay? That being said, from the people that did distribute, most of you started there and then distributed the 5x cubed at the end. You could have started here, just distributed that to a binomial, and then whatever that answer was, multiplied it by the 3x squared minus 7. Here's the way I did it. See, I did that. I distributed the 5x cubed first, just to the first one, got my 10x to the 4th plus 5x cubed, and then I went ahead and FOILed, or double distributed, whatever you call that. And little things with exponent rules, like an x to the 4th term times an x squared term comes into an x to the 6th term. So definitely some work that needs to be done there. Some polishing, which we will do. Okay, if I collected your paper, I'm going to hand them back and just hand the stack over to this, and then you can kind of grab yours and then send it behind you, because I got a couple of theirs. And then Vince, I have yours in there too, right? Then we'll send Vince's over to him. Any questions? Don't worry, every day won't seem this long. You're just literally here for an hour. And I'm capitalizing on every second of it. All right, so number 3. Who can look at that right away and tell me the twist? What does everybody forget to do, Olivia? Double distribute. This is a scenario where a lot of people will make the mistake of squaring this, calling it a day. And that would be incorrect, okay? when you are squaring a polynomial, which is something that's more than one term, separated by pluses and minuses, you have to expand, and hopefully we get to a place where we don't have to expand, but meaning we don't have to write it down, we can kind of visualize on our own. But for now, that's what we're expanding and visualizing, and then that double distribute. 5x times 5x, 5x times negative 3, 5x times negative 3 again, and negative 3 times negative 3, positive 9. So when we combine like terms, we have our final answer. So if people squared this right out of the gate, that incorrect way that I was referring to, they would get the 25x squared. They would get the 9. Maybe they would have had minus 9. It should be a plus 9, obviously, because the double negative being multiplied. What could be the shortcut? If we wanted to kind of eliminate that, what could we do and think that, how does this negative 30 arise? If we wanted to kind of get out of the habit, because we're going to have to do this a lot and it just takes more time, and I'm all about being efficient. If we wanted to get rid of these two steps of work, obviously we can get the 25x squared with the first term, then plus 9 with the last term. Where could we get that negative 30 from? Right, you just multiply these two together, and you're doing it twice, because your outer two terms give you negative 15x, and your inner two terms are always going to give you the same 2, negative 15x again, and so it really just ends up being double that product, right? These two multiply to get negative 15, double that, negative 30. And we'll work on that shortcut more as the year goes on. All right, in 4, A is not a number anymore. A is a polynomial, a trinomial to be exact, and B is a trinomial. So absolutely here, because when you are doing subtraction, if you're subtracting a trinomial, you 100% need your parentheses around those substitutions, because you're subtracting multiple terms, not just the first one. So we'll plug in first the A minus, plug in our B, and then this distributing is huge. We're not just subtracting 3x squared. We're not, if you don't put parentheses there, it looks like you're just saying minus the 3x squared. That's not the point. You're subtracting the entire B, which is every single term of that trinomial, which means that negative has to be distributed. This set of parentheses had nothing in front of it, so not that big of a deal. We don't really need to write those anymore. When we distribute the negative, we get negative 3x squared. The double negative on the 6 turns it into a plus 6x, and then a minus 1. And then we'll just combine like terms. Our squared terms first, we have 5 of them. Our x terms, we have 13 of them. And our constants, negative 5 and negative 1, makes negative 6. Nothing new, right? Just a little bit more complex than Algebra 1. Algebra 2 is like a lot of the tougher problems from Algebra 1. It's not that you've never seen them before, it's just the harder ones kind of become the norm. Raise your hand if you know what an identity is in math. Not like your identity. An identity? Anybody? I'll give you an example. 7 equals 7. That's an identity. 12 equals 12. That's an identity. Remember if you were solving an equation and you got down to the end and you got 5 equals 5? What would you say is your answer there? All solutions? Does that sound familiar from Algebra 1? Okay, so you'd get like all solutions, or it's an identity, because no matter what x is, both sides will always be the same. So we're going to prove identities a lot here. It's a theme throughout. When we look at trig functions, which sounds foreign to you right now, when we look at rational functions, when we look at exponential log functions, which you've probably never heard of before or have any idea what that is, all these types of functions, we're going to be working on identities as a common thread through all of those. So I figure on day one, let's just use our simplifying practice as a way to kind of explore what an identity is. You're trying to prove that this equals this. So all that is, and this is your three-step process, simplify the left, completely separately, like pretend the right-hand side doesn't even exist. Simplify the left. Then pretend the left-hand side doesn't even exist and simplify the right. And if they're telling you to prove the identity, they should be equal. You're just showing it step by step by step. So you really have to be adamant about showing each and every step in your simplifying process. So let's see what happens here. Within the brackets, I'm first going to distribute that 6. So it's going to create 6x squared. And here I'm going to kind of combine two steps in one, if you'll bear with me. This is a minus 12, but I know I'm then going to combine it with a plus 5. Does everyone see that? Negative 12 plus 5 gives me negative 7. Keep everything else the same. Now I'm going to distribute that negative that's in front of the brackets. And now I'm going to combine like terms. So I have 12x squared plus 11. That is my left-hand side, simplified. Now, almost as if it's a totally separate problem, we're going to simplify the right, which requires a distribution on the first term, requires the distribution of the negative 5 on the second, and a distribution of the 6 on the last. So go ahead and do that and kind of check your work with me. You don't have to copy what I'm doing because this is pretty straightforward. Just use what I do to check your work. Once those distributions have taken place, you can go ahead and combine like terms. So I've got a 6x squared plus a 6x squared, which is 12x squared. I've got a plus 15x minus a 15x, which is a wash, gone. And I've got a plus 5 and plus 6, which is plus 11. Do those sides equal each other no matter what x is? Always. Yes. That's an identity. Usually with an identity, you'll do like a little check mark. It's literally like an algebra version of a proof. Very different than geometry proofs, yes? Okay? Very different. Here's the biggest thing with proving identities that you can't ever do. You can't do anything that you would really do in a solving process. What I mean by that is you don't ever like subtract 7 from both sides. That's a solving technique, okay? With an identity proof, you are literally treating it as two totally different problems, simplifying the left, simplifying the right, keeping your fingers crossed, praying that they're equal, okay? But if you start moving something over, even though if I subtract 11, it will still say 12x squared equals 12x squared. You've subtracted 11 from both sides and assumed that they're still going to be equal, already assuming that they were equal. It's a weird concept. Just don't do it, okay? Never do the same thing to both sides when you're proving. All right, so we'll skip this one just because we probably only have time for one more. This one kind of asks you to figure out what A, B, and C would need to be to complete the identity. So just asking about an identity from a different vantage point. We're still going to simplify whatever we can, so that would be the left-hand side. Can we try and practice using that shortcut for a minute? Rather than expanding, what's my first term going to be and why? Georgia. gave me, you multiplied the two together. Who can tell me what the, we'll come back to it. Who can tell me what the first term is going to be? 9x squared, which he gets just by doing 3x times 3x, right? Who can tell me what the middle term is going to be? 24 minus 24, yes? So 3x times 4 is 12x, and then we're going to double that, minus 24x. And then the last term, who can tell me? Go ahead. Positive 16, very good. We can't really simplify the right. Oops. But we're pretty much done. What does A have to be to complete this identity? 9. So A equals 9. What is B? Negative 24. And C is 16. It kind of just exposes itself. So back to that squaring. What I was trying to kind of get us to start thinking about is how can we come up with this square without actually expanding it. But when you expand it, can you see now why that first term is a 9x squared, why the last term is a plus 16, and then when you do the outer negative 12x and the inner negative 12x, it kind of doubles that to negative 24x. Okay? I don't waste a minute. Hold on. Just really quickly, and you can just watch this, but just kind of sit still there for a minute. I do have to square this, right? I can square this binomial by using that shortcut. The first term squared is going to be what? X to the 4th. If I multiply these two, I'm going to get x squared y squared. And I'm going to double that, so it's going to be 2x squared y squared. And then the last term is going to be this squared, which is y to the 4th. What is 2xy squared? See, this was a polynomial, two terms, a binomial to be exact. This is a monomial. So I literally can, quote unquote, distribute that squared to each piece of the single term. 2 squared is 4, x squared is x squared, y squared is y squared. Yes? And then on my last term, it's a binomial again, so I square that, x to the 4th. I multiply them together, I get x squared y squared, and I've got two of them in it, and it's a negative, 2x squared y squared. And then square that last term plus y to the 4th. That might be a little bit of a stretch squaring those in our head, just because of the letters that are involved, the variables that are involved. So expand those if you have to. That's absolutely probably where you should be right now. Papers are coming back. Take one. And bring your own calculators tomorrow because I a whole parade back and forth there. Alrighty, it will never be this long again. Ever, ever.